We've eagerly anticipated this moment as physicists for more than a century. Since 1916, this occurrence has been a groundbreaking accomplishment, providing an inside look at one of the most mysterious and fascinating phenomena, black holes. These cosmic giants are famous for their immense power, yet they continue to be extremely elusive. Despite their enormous size, their gravitational pull makes them almost unnoticeable to us. What makes them even more enigmatic is a similar black hole, possibly weighing between 2 and 4 million times the mass of our Sun, which is the focus of this investigation. Over the past few decades, research on black holes has changed our comprehension, taking us from a position of complete ignorance to one where we are beginning to understand them more intimately. This has made a career as a physicist even more exciting. Michio Kaku has made it clear that we have succeeded in peering into a black hole. This breakthrough opens up a wealth of new information that may provide insight into aspects of science we previously overlooked. Let us examine it thoroughly, plunge into the depths of the black hole, and discover what they contain. While the concept of space is vast and boundless, black holes generate numerous questions. Before we begin discussing the remarkable findings of Kaku, understanding the fundamental properties of black holes is essential. Most people have at least some comprehension of black holes, however, significant knowledge gaps persist. The idea of black holes originates from 1916, when Albert Einstein released his general theory of relativity. This theory predicted the existence of black holes, but at that point, the concept was only theoretical. It was not until approximately 50 years later, in the 1960s, that tangible evidence for their existence first became apparent. Researchers examining the constellation Cygnus made a peculiar observation, a bright blue star emitting X-rays. They discovered that the star was not stationary but instead orbiting a massive black object. After further investigation, it became evident that these X-rays were being absorbed into this object, leading to the term black hole. This finding was a historic turning point, as it demonstrated that black holes were not simply an invention of Einstein's imagination, they were real, physical entities existing in space. Researchers from all over the world began concentrating their studies on a particular black hole within the Cygnus constellation, designated Cygnus X1, located about 6,000 light-years away. This black hole, far from Earth, was approximately 14 times as bright as the Sun and exhibited an immense density and gravitational pull so strong that not even light could escape it. This defining characteristic, the ability to ensnare light within its gravitational grasp, makes black holes both fascinating and terrifying. A black hole is a region of space where gravity is so powerful that nothing, not even light, can escape. Any object that ventures too close will be sucked in and, upon reaching a critical threshold, will vanish forever. Because of this inherent danger, improving our comprehension of black holes is crucial. Following the discovery of Cygnus X1, researchers embarked on an extensive search for additional black holes. Current estimates indicate that there may be over 100 million black holes scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are extremely challenging to detect, making an exact count nearly impossible. One thing remains clear: millions of black holes could exist in our galaxy, underscoring their significance in cosmic research. One of the principal concerns regarding black holes revolves around the force of their gravity. It is so great that anything approaching too closely is gradually stretched to an extreme point, ultimately collapsing into a singularity. Simply put, black holes act as cosmic vacuum cleaners, pulling everything in with an unstoppable force. A particularly concerning aspect of black hole research is the phenomenon known as spaghettification. If an object, or even a person, were to fall into a black hole, they would be stretched into an elongated form due to immense tidal forces. This process would be gradual, and the individual would perish before reaching the final stage. Thus, it is clear that avoiding black holes at all costs is imperative. Despite the fact that the closest known black hole is approximately 500 light-years away, scientists still ponder the potential threats they may pose. In 2021, a significant milestone was achieved when scientists successfully captured the first clear image of a black hole. This particular black hole was situated in the M87 galaxy. Over several nights, the research team took numerous images and combined them into a comprehensive picture, revealing surprising details. Contrary to the common misconception that black holes are simply vast voids, they consist of 3 distinct layers. The first is known as the event horizon. Once crossed, there is no return. The second layer, the photon sphere, is a region where light can be trapped in orbit. Any light entering the black hole must circle around it before being inevitably drawn inward. The final layer is the singularity, the point of infinite density where the known laws of physics break down entirely, making it impossible to predict what might occur. Even more intriguing is the fact that no two black holes are exactly alike. While they all adhere to this three-layer structure, their behavior can vary significantly. Typically, astronomers study celestial objects by observing them through telescopes, but this approach is ineffective for black holes, as they are invisible. Instead, scientists must study them indirectly by analyzing the radiation, gas, and dust surrounding them. Voyager-class probes exploring a black hole remain out of the question, as anything crossing the event horizon is inevitably pulled into the singularity and destroyed. As a result, scientists must rely on indirect observation techniques. Despite being three-dimensional objects by nature, black holes are often analyzed through a two-dimensional lens. One prevailing theory suggests that black holes form as a result of stellar collapse. When a massive star exhausts its nuclear fuel, it can no longer generate enough energy to counteract gravity, leading to an implosion that eventually creates a singularity. In an effort to better understand black holes, NASA scientists focused their research on the M87 galaxy's core. There, astronomers observed an enormous whirlpool of hydrogen gas spinning at an astonishing 1.2 million miles per hour. The mere force of this gas should have caused it to break apart, yet it remained intact. Scientists theorized that a massive, unseen object, potentially weighing between 2 and 3 billion times the mass of the Sun, was holding it together. The only plausible explanation was the existence of a black hole. Black holes can form in various ways, including from collapsing stars. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the dynamics of a rotating black hole. Kerr's solution demonstrated that instead of collapsing to a single point, a rotating black hole could create a thin disk known as the ergosphere, where physics begins to break down. Kerr's work also predicted the existence of the Einstein-Rosen bridge, commonly known as a wormhole, a hypothetical tunnel linking two different points in spacetime. Bridging the gap between quantum mechanics and general relativity remains one of the most significant challenges in modern physics. While Einstein's equations provide a strong framework for understanding black holes and spacetime, they do not account for quantum effects at the subatomic level. To truly comprehend the nature of black holes, wormholes, and the fabric of the universe, physicists must develop a theory that unifies general relativity with quantum mechanics. One promising avenue of research is string theory, which suggests that fundamental particles are not point-like but rather tiny, vibrating strings. This theory attempts to reconcile gravity with the other fundamental forces of nature. Some variations of string theory propose the existence of extra dimensions, which could help explain the nature of black holes and their interactions with spacetime. Another potential breakthrough lies in quantum gravity, a theoretical framework that seeks to describe gravity according to quantum principles. One of the leading candidates for such a theory is loop quantum gravity, which suggests that spacetime itself is quantized, consisting of tiny, discrete loops rather than a continuous fabric. These emerging theories may provide answers to long-standing questions about black holes, including the information paradox. According to classical general relativity, anything that falls into a black hole is lost forever. However, quantum mechanics suggests that information cannot be destroyed. This apparent contradiction has puzzled physicists for decades. In the 1970s, Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Over immense periods of time, this radiation would cause black holes to gradually evaporate. The fate of the information trapped within the black hole, however, remains an open question. Some physicists argue that information is preserved in a highly scrambled form on the event horizon, while others suggest that it might be encoded in the Hawking radiation itself. Recent advancements in observational astronomy have furthered our understanding of black holes. The development of the Event Horizon Telescope, EHT, allowed scientists to capture the first-ever image of a black hole in the galaxy M87. This groundbreaking achievement confirmed key predictions of Einstein's theory and provided direct visual evidence of a black hole structure. The bright ring seen in the image is created by light bending around the event horizon, revealing the immense gravitational effects of the black hole. Additionally, gravitational wave astronomy has opened new frontiers in black hole research. The Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo Interferometer have detected gravitational waves, ripples in spacetime caused by the collision of massive objects, such as merging black holes. These discoveries have provided invaluable data about black hole mergers, their masses, and the nature of their interactions. The detection of intermediate mass black holes, which lie between stellar mass and supermassive black holes, has also shed light on the evolutionary processes of these cosmic giants. Beyond their scientific implications, black holes continue to captivate the human imagination. They are central to numerous science fiction narratives, often depicted as gateways to other dimensions, time travel, or even alternate universes. While these ideas remain speculative, the possibility that black holes could serve as cosmic portals is a topic of ongoing theoretical investigation. Looking ahead, future advancements in technology and space exploration may allow us to probe black holes more directly. Proposed space-based observatories, such as the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves with unprecedented precision, potentially unveiling new details about black hole dynamics. Additionally, advancements in quantum computing and artificial intelligence may enhance our ability to simulate and analyze the extreme physics of black holes. In conclusion, black holes remain one of the most enigmatic and fascinating phenomena in the universe. Their study has revolutionized our understanding of gravity, space-time, and the fundamental nature of reality. As research continues, we may uncover even deeper insights into the workings of the cosmos, pushing the boundaries of human knowledge and unlocking the mysteries that lie within these cosmic behemoths. The theorem is known as might be explained by a theory of everything, how everything in the universe works on every scale, from the tiniest particles to the largest structures of the universe. Michio Kaku, a leading theorist in theoretical physics, has been developing this common theory for decades. A potential candidate is the superstring theory, which holds that fundamental particles are, in fact, extremely small vibrating strings. In this framework, the universe is viewed as a concerto, with various particles corresponding to variations in these strings' vibrations. Superstring theory additionally offers possible justifications for black holes, wormholes, and other bizarre phenomena, demonstrating how strings influence the fabric of spacetime. Despite its potential, superstring theory remains highly speculative because it requires additional dimensions of space and time that we can't directly observe. These extra dimensions could be so small that they are effectively unseen. According to some theorists, these dimensions were less numerous at the start of the universe and gradually curled up as the universe expanded, reducing their influence. Consequently, the potential of superstring theory to explain wormholes, black holes, and the universe's very fabric remains one of the most exciting frontiers in physics. As we continue to decipher black holes and their mysteries, it is evident that we are only scratching the surface of understanding reality. Michio Kaku's work in string theory, quantum gravity, and related fields offers potential solutions to these cosmic mysteries. Although technological advancements, such as the Event Horizon Telescope, have provided greater clarity on black holes, indirect observations still leave many questions unanswered. Our comprehension of theoretical physics, particularly within the context of spacetime, remains an active field of study. Black holes are now at the heart of discussions about the universe. String theory suggests that universes might collide, potentially leading to the formation of new ones, with black holes playing a crucial role in this process. This idea implies that the universe we know today could have emerged from a collision between two earlier universes, or even that we exist within a black hole neighborhood. If true, this concept would fundamentally change our perception of the cosmos. While black holes are often viewed as destructive, they might also serve as gateways to parallel universes or other realms. The notion that black holes could facilitate time travel or interdimensional travel remains an intriguing area of speculation. However, the internal workings of wormholes and their feasibility as traversable passages remain in question. Even if wormholes could theoretically form, the extreme radiation and gravitational forces near them might render them inaccessible. Some physicists hypothesize that if a wormhole could be stabilized, it might allow travel between distant points in the universe, but this remains purely theoretical with our current technology. Examining black holes through the lens of quantum mechanics presents even more fascinating challenges. Quantum behavior at a microscopic level differs fundamentally from our macroscopic experiences, leading to apparent breakdowns in physics when applied to black holes. The long-standing incompatibility between general relativity and quantum mechanics remains one of the greatest hurdles in modern physics. Superstring theory offers a potential framework to reconcile these differences by introducing new dimensions and fresh perspectives on gravity. However, it has yet to be tested, and many of its predictions remain unverified. Kaku and other theoretical physicists continue working toward a unified theory that merges quantum mechanics with general relativity. Such a theory of everything could deepen our understanding of black holes, the universe, and even spacetime itself. The idea that multiple dimensions exist, predicted by string theory, could help explain hidden forces shaping the universe. If true, our perception of a four-dimensional reality may be just a small part of a much larger, more intricate structure. Another area of intense research is the role of black holes in galaxy formation and evolution. Scientists have discovered that supermassive black holes exist at the centers of most galaxies, including our Milky Way. This raises questions about their impact on star formation and the overall structure of galaxies. Some researchers hypothesize that black holes regulate galaxy development and even influence the universe's fate. Their powerful radiation, known as Hawking radiation, named after physicist Stephen Hawking, has sparked debates about what happens to information that falls into a black hole. The information paradox questions whether data is permanently lost upon crossing the event horizon. Hawking suggested that black holes emit radiation, causing them to gradually evaporate over time, potentially resolving the paradox. However, this remains an open question in physics. Regardless, black hole research has provided profound insights into gravity, space-time, and the universe itself, pushing us toward a new frontier in physics. As our observational tools improve and we explore both quantum mechanics and relativity, we will likely uncover even more surprises, reshaping our understanding of the universe in the process.